Last time we learned that chatbots work by using probability and statistics. But what is all of this and how does that work? What are the nuts and bolts of chatbots and how come modern chatbots are so much more effective than what they used to be? Well, we're going to find that in part 2 of our chatbot series. So today we're going to start with some chatbot history. Can you think of maybe the earliest time that chatbots might have even been thought about or been around? Well, I'm going to argue that it's this another old Greek dude called Daedalus. And Daedalus, as you may know, was the father of Icarus from the famous parable where he, flies too high and then falls from the sun, or maybe is just very bad at making bird wings. Now, this person was supposedly responsible for all kinds of different kinds of inventions, including things like moving statues. This is attested to in different Greek authors, but not necessarily ones that were around at the same time. So it seemed like he made things that seemed to be moving, and he probably also did. Of course, this is accomplished with just mechanical types of things, and I argue that chatbots are just a special version of like an automaton type thing. But did you know that the Greeks actually had really old kinds of computer looking things? One of this was called this Antikythera mechanism, and they found this in an ocean like maybe 130 years ago, and supposedly it was used to capture and calculate things like the orbits around the sun of the various known planets at the time. Here's a version that shows some kind of modern reproduction. So you kind of turn the crank, you can figure out different things you might want to know as a Greek person in terms of the signs in the sky. Pretty interesting, really. And actually much more complicated than you would suppose because of the way that our planets orbit the sun. Now, you have to go forward pretty far from there, sometime around 1850, and think of the analytical engine. This is invented mostly by Charles Babbage, this guy here. And he also has an autobiography where he talks about the future. What if I had infinite time? Kind of like Iron Man's dad, maybe, who said that he was just born for a different time. Anyway, these were precursors to things like the Enigma machine for breaking down the codes created by Nazis during World War II and all of that stuff. And it's definitely the precursor to our modern technology, our modern computers. So all of these like fancy diagrams, Charles Babbage was mainly doing things like making looms automatic, designing patterns inside of woven fabric. And interestingly, as a polymath, he was a mathematician, a philosopher, an inventor. Sometimes they used to call these like a Renaissance man, a Renaissance person. And that basically just meant that you did all kinds of things and you didn't really know what kind of field there was. And all of these fields were not segregated and kind of like closed off from among each other like they are these days. Now, while many people consider Charles Babbage to be the father of the computer, and he made this computer and a difference engine, difference meaning like really hard subtraction, he also has an autobiography, which is a very strange read, if I'm going to be honest. And in that, he talks about other kinds of things, like what if you could figure out exactly how to create a game based off of an automaton? Could you make some rules and some machinery? So it would be like kind of fun to actually have this adversary. So these ideas of creating something that almost seems human, that can play the same kinds of games that we play, these have been around for a very long time. This is again like 1850. Around the same time, Ada Lovelace, who's considered to be like a really great mathematician, and she basically had this idea of, hey, this isn't just for subtraction. You could do just about any kind of computation for that. One of the computations that she did was actually the Taylor series. Is this it? There it is. That might be it. I think that's it. Where is it? Yeah, I think this is the diagram that shows how you would calculate the Taylor series. This is like an advanced kind of math thing. And it's like, oh, do I really want to do all of this work here to calculate this thing, then that thing, then this thing? And all of these things kind of combined together. They're not particularly difficult to do. They're just sequences of operations. And as we know, computers and machines actually happen to be really great at doing that. Now, this brings us to a name that we've heard before. Alan Turing. Remember the Turing test we looked at in class? Well, Alan Turing also designed, it's a sort of a theoretical, but actually a literal kind of computer. And in computer science, oftentimes if you have like a real programming language, it's known as Turing complete. This is an example. And in that model, you have a giant tape which serves to be memory, and I'm actually not going to explain it, but if you're interested, you can take a look at it. And basically, there's these different levels of actual computers, and defining what those are and how they work evolves into much more complex and complex systems. For example, did you know that there's something called the halting problem? And if you have a programming language that is actually Turing complete, that is, it basically could be classified as a Turing machine, then you can't write a program that will be able to analyze a program to know if it will stop or not. And so, I mean, these things were extremely generalizable compared to something like the differential engine. And so here is one of Turing's papers that we looked at before, where he talks about this Turing test. And on this Turing test, Alan Turing describes, how could we come up with a really, really hard test for in the future when we have computers that are amazingly good at kind of pretending to be people. And the way he looks at it is kind of like an observational scientist. So he talks about using these kinds of questions as specimens. For example, please write me a sonnet on the subject of the fourth bridge. And the answer might be, count me out on this one. I could never write poetry. Now, if you imagine this in like a very British voice, Alan Turing was British, it sounds kind of funny. Add this number, 34,957, to 70,764. Yeah. Then maybe it pauses for 30 seconds. Can you imagine your computer taking 30 seconds to do this? I don't know. Do you play chess? Yes, I play chess. No further. Oh, okay. I have K at this and blah, 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 blah. How do you play? Okay, I'm going to move this. So this is like a chess puzzle. Can this computer actually solve these questions? Well, Alan Turing at the time, this is 1950, says, I don't think we can do this yet. But something came up not super long after that, about 15 years later. We had Weizenbaum create this thing called ElizaBot. And ElizaBot, it kind of, it could answer questions, and it could ask them and answer them kind of like this, right? And essentially, it's kind of like a magic trick. It's kind of like an illusion, sleight of hand. So here's a typical conversation. This is the user. Men are all alike. In what way? Says the computer. They're always bugging us about something or other. Can you think of a specific example? Says the computer. Well, my boyfriend made me come here. Your boyfriend made you come here. So instead of actually having to do any thinking, which is really, really hard in 1966, we can instead just write a bunch of phrases that people say that have to do with kind of the syntax and the protocol of the time. How are you doing? I'm fine. How are you doing? I am also fine. These kinds of very robotic, classically robotic kinds of speech. Now, in the back, they list all of these different phrases, and so you can actually code up one of these bots on your own if you want to. There's several clones online. And essentially, it's looking for trigger words, keywords, kinds of ways that people do phrasing, and it's surprisingly effective. and it must have been mind-blowing in 1966. So let's start looking at a little bit of our history here. We had in around 200 BC, moving statues. We had in the 1850s, like a difference machine. We could also place on there Ada Lovelace. I'm just going to write Ada there. Like idea of general computing. And then, much later, we had new things come in, and these new things were actually pretty transformative. I don't remember if I went over this last time about computers, but we'll do it anyway. So in the 1950s, we had digital computing. We had something called a transistor, which I will represent like this. And the digital computers basically took the idea of you have to have these big, mechanical gears, analog things, all the way from this this crazy old thing for showing, where the planets are going to be. All of that got turned into like ones and zeros using either vacuum tubes, which were a precursor to a transistor, or a transistor. Now, essentially the way that these work are by having lots of different kinds of possibilities at the same time. So a computer has lots of bits. These bits can either be on with a 1 or off with a 0. And like I mentioned, I think last time, you can represent even analog data if you have enough bits. And it makes computation things much, much easier. So much so that by 66, by 1966, you had Eliza Bott. And believe it or not, in some cases, the people who are using this would actually fail the Turing test. They wouldn't be able to know if they're talking to a real robot psychologist or just a really stale, not very empathetic psychologist. So these are all pre-modern, and you are probably most familiar with something called ChatGPT. And the biggest breakthrough came about because of the transformer. And the transformer was discovered or invented or whatever in 2017. Now, there are other things that probably you could attribute to being close to revolutionary, but the transformer is still kind of the gold standard that modern large language models like ChatGPT or Gemini use. Then in 2019, you had GPT-2. This was a pretty good model. It was good enough where people started to think, if people just posted all the content that gets created from this, maybe they wouldn't be able to know whether it's true or false. Then we had Instruct GPT. We're going to call that 2022, maybe 2023. But this basically is really just a ChatGPT, which, as you may remember, was quite revolutionary and kind of let the normies in on the thing that there are really cool AI technologies. But kind of in between, there's this kind of like interstices place. And just to help people understand what's going on here, we're going to look a little bit about something called a Markov chain. Now, a Markov chain is basically the idea that any state that you're in, you can multiply by some big matrix, and then it can tell you what new state you're going to be in. In this scheme, we're going to use states like words and maybe previous words. So for example, we have the dog, the cow, and the pig. And we can kind of build up a table of probabilities based on where we were. So for example, we can move these to like a table. So if we're on the word the, basically we are going to be transitioning to one of these at a third of the possibilities, and we're going to be transitioning to the 0% of the time. If we're on the word dog, well, in that case, the only word that ever comes after dog is the word the. So we're just always going to go across here. Same with cow. Same with pig. And you could come up with something pretty easily by essentially just running through and taking each one on its own and trying to position the next word based on where you were. In this case, we have 4 possible words, and I actually kind of coded something up like this, so let's see how this works with a little bit more data. So this is Dr. Seuss, and Dr. Seuss has a lot of different commentary like this, and we can copy some of the words here and just get a good feeling for how this could be interpreted by a very simple text generator, which we're using, called a Markov chain. So if I copy this text, I put it in my my program here, I hit calculate probabilities, well, then we get all the different words. We get things like quotes, I, the, and the total count of them. And this whole probability column would add up to the number 1. The other interesting thing is if you actually take the last word, let's say a word that happens a lot like I, then it gives you the probabilities of these other words here. So I know is the most, then I will, then I do. And just using this simple table, this simple information, what can we do? We can generate things. So if we're generating based on bigrams and we generate 10 words at a time here, we hit a few. The first word is mother, then will, then show them to you. Your mother will show them to you. Your mother will not mind at all if I will not mind. So it almost, and we can look at a different version of this. It feels a little bit like Dr. Seuss, right? Mother will show them to you. Your mother will show them to you. Your mother will not mind at all if I will not mind at all if I. We can generate more of these, right? Just going to do a whole bunch. And you can compare this to things that you could see in, say, ChatGPT. We will just adjust this a little bit. So, mother will show them to you. Your mother will show them to you. I know some new tricks, said the cat. A lot of good tricks. I will not mind at all if I do. So it's just kind of this bizarro kind of thing, and it's very, very simple math, just like we just did in our example right here. So, if something so simple is effective, why do we even need ChatGPT and GPT things? So there's a lot of problems with these text generation things, especially if you're taking this fairly naive approach. One of the problems is like completing things. So for example, if you have a quote here, you want to always, always, always have a quote at the end. Same thing with like coding. If you have a curly brace, you also want to have a curly brace at the end. And some kind of things before the transformer actually did accomplish this pretty well. Things like an LSTM, which is actually one of the components that goes into the transformer. Now, let's talk a little bit about transformers and what the actual physical machinery looks like for things like ChatGPT. We'll do that at the end. Let's just get into some of the results of some of these kinds of papers. The first one we're going to take a look here, that language models are unsupervised multitask learners. This was a revolutionary paper from ChatGPT 2, and it formed kind of the basis of a lot of the funding and stuff that this amazing company, OpenAI, did. And essentially what they did is they put a lot of data into their models, and it kind of did like a guessing game. And by doing that, they're able to guess generated answers by like, who wrote the book of The Origin of Species? Who is the founder of the Ubuntu project? Who is the quarterback of the Green Bay Packers? So instead of having to actually write a chatbot by just doing a very advanced version of a sort of a Markov chain, they're able to invent these general answers. So you can ask the computer basically anything and it gives you the correct answer a lot of the times. Maybe 80% of the time. It's much, much, much better now compared to how it used to be using ChatGPT 2, but this really showed a ton of potential promise. Now, one of the things they actually talk about in this paper are results. And this is basically based on if you start with a big starting point, then the completion depends on how big the model is. How complex the model is will determine things about how great it generates things. And these are pretty convincing if you read them, but not nearly as convincing as the even more modern ChatGPT type things. The other big paper from 2022 is ChatGPT, and they called it Instruct GPT. Now, in this case, they're greatly increasing the model size up to 175 billion parameters, which is still a pretty big model by today's standards. And they're retrofitting some high level version to do the actual tuning, where instead of just having to start with a whole bunch of prompt, can you start with just a little bit of a prompt and get a big, good, as you sort of expect it, sort of a response from. And, this is the part of the paper that explains the different aspects of their training. So in step 1, way over there, what happens is they collect a whole bunch of data, and they basically just do the standard GPT-2 type thing. It's literally the same stuff. But one of the things that they do is they actually bootstrap that. Once they have that, they actually have this big data set of prompts. And from this big data set of prompts, where people are typing and the computer is doing what they want, then they have a human labeler, someone actually going down and writing down, hey, this was good, this was bad, this was whatever. And they're using that to create a new GPT-3 that is more of like a supervised learning type thing. Next, they use that model and create a whole bunch of examples, doing slightly different probabilities on the actual text. And then finally, they create a whole new AI that is able to kind of pretend to be a person rating the quality of the responses from ChatGPT. This is all pretty complicated, and so that's okay. And so ChatGPT has had all of these different versions over the years. You can look at the Wikipedia article if you're very interested in it, but basically it really took off around 2023. And this talks about some problems which you may or may not be familiar with, which we will go over at some point in the class, including hallucination, where an AI doesn't actually know what it's doing. It's just computing. It's literally just like a GPU somewhere, and doing its very best. This is Sam Altman. That's the CEO of OpenAI, who does this kind of work. And so at this point, we are into GPT 5.1. This is November sometime, and this is November 12th. And there's all these versions that you kind of, they are not even really supported anymore, but there are also open source versions of a kind of ChatGPT, which we may or may not talk about in this class. Okay, moving forward. The thing that really makes this possible is called a transformer. Now, you may remember from the Markov chain, should we look at that a second here? It creates all of these different possibilities based on the current word that we're on. So for the word no, we have a probability of 0.5 here, and then will is 0.25, and then do is 0.25. Well, the sort of the backbone of the way that these large language models work are called a transformer. And this is a visualization of what's actually happening physically. So the computer has this digital machinery inside of it that does all of these multiplications and things. And it starts with this data here. This data right here. Visualization, EM powers users 2. All of these are basically sequences. And these sequences of words get turned into little bits of data that exist in some kind of a space. And the space is literally just numbers, similar to that thing we did with the cow. Now, you could keep generating things, or you could see that this is actually a bunch of transformers stacked on top of each other. But at the very end, if you had the words data visualization, M powers users 2, then your most likely word you're going to actually pick would be visualize. then it would be create, then see, then make. So if you think about it in your head, data visualization empowers users to visualize. Data visualization empowers users to create. Data visualization empowers users to make. All of these words at the end, they could all work there. And that's how these things work. They're just trying to guess the next best word based on what they currently have. And, it's interesting too, because even at ChatGPT 2, the samples that were created, they showed some concerns that maybe flooding the internet with what's now called slop is maybe not the best idea in the world to do. And so they published a blog about it. And they didn't release the biggest versions of their code. They're just releasing some of the data sets and the training weights and the smaller versions of GPT-2. Okay. So the basis for the data that actually goes into these GPTs is just based on guessing words. And you can base words that you want to guess based on having a lot of words. We did that already using Cat in the Hat, and it basically just uses a more advanced version of that, where you have both the word that you're currently looking at and maybe a couple of words behind and a couple of words ahead, and then you're trying to guess what that word kind of in the middle is. So when a computer actually sees words, they're not seeing them the same way as you or I see them. Instead, they might be seeing little parts of them. That's why in this version, we have the word M and the word powers, even though this is one word to us, this is two words to the computer, or two tokens. So I want to go over just a little bit of this terminology, and that will be enough of learning about how this works for today. So let's talk about the actual nuts and bolts here. Nuts and bolts here refers to like the actual mechanics of the things happening underneath the thing that's happening. And basically, if you wanted to create your own large language model, you would need 4 different things. The first thing you would need is data. Then you would need some complex digital machinery. Then you would need compute. And finally, you would need some clever training. Now, for the data, usually places like ChatGPT, they could gather data from a lot of different places, including the internet, books, social media. You just want lots and lots and lots of data. You also need some complex machinery. For example, you might need like a big neural network, LSTMs, transformers. These are all kind of like internal representations that can go from a bunch of different text that might look like this, and then chop it up into a bunch of different pieces. And eventually this actually is just meant to feed a machine. There's an input and there's an output, and the output outputs tokens, and the input inputs tokens. And then over here, literally inside what it looks like is something like a whole bunch of dots, kind of like the internet, all connected in different ways. And then how those are actually connected, it starts off just random. But when you add in that compute, what ends up happening is it almost creates a brain-like structure where clever, smart, kind of the right guess tokens get created based on that input. And then you need some smart training schemes, right? So oftentimes if you only train it on internet, you just get internet. And we have this phrase in computer science called garbage in, garbage out. If you only take in garbage, you only get garbage out. And that's why things like including the right kinds of data is so important. So if all you ever feed your large language model is only data from one country in the world, well, it's probably not actually going to learn a different language. It probably wouldn't learn about all countries' cultural norms, and you'd probably be missing out on quite a bit of stuff. Similarly, if you never gave your LLM anything from books, maybe everything would just look like it was written on the internet. And there's other issues in data and selecting that data, which I will not get to today, but just think about it a little bit. So now that we know some of these internal mechanics and how things work, let's talk about more terms for the chats that we use, maybe even on a weekly or daily basis. So some of the basic things are things like text. What is text? That's like writing, Dr. Seuss stuff. So if I said something like the cow, the pig, the dog. That's all text. It's all just a string of characters. Tokens are a little bit different. That would be like the is a token, cow is a token, comma is a token, the is a token, and on and on and on. A sequence is basically all of these things strung together but represented by tokens and not words per se. And as I mentioned a little bit beforehand, really these tokens, sort of on the inside, they kind of look more like this. They might look like some numbers, like a 0 and a 2, on and on and on. And there might be something like 1024 of these numbers that represent that particular word concept. This makes it easier for the computer to do things like compare the word cow to the word bovine instead of having to use only the actual words. Then we have a prompt. The prompt, this is what the user says. And the response, this is what the system says. The system being like ChatGPT, things like that. And what's interesting is that you can actually go prompt, response, prompt, response, prompt, response. And hopefully that's what you're doing now in this homework. And there is a little bit of a problem because at some point, how much information you're giving the actual system might become too much for it. So this is sometimes called a context window. And it has to do with how much information from the past the system can look at to predict the future. And by predicting the future, I mean predicting what tokens it should spit out next. Now, there's a couple of other things that are brand new that I won't talk about for now, but I do want to say that these models are tremendously good and interesting and good at picking up both explicit context and implicit context. We will talk a little bit about what makes a good prompt and what makes a bad prompt. Here's a little preview. We'll just talk about it. A good prompt is like good communication. It's where you explain everything that you want and you give it step-by-step detailed information so that it can create a response that is based off of that information. Oftentimes what happens is you might ask for something and it provides it in one of these responses. Right? So you might say something like, write me a poem. It writes you a poem and then you say that's too long. And then it says, okay, here's a shorter one. And then you say that's too short. And then it gives you finally the poem that you actually want. And the only reason it actually knows how long you want the poem has to do with the context from the previous times that you talked about. And so in most of the time when we're having conversations, we pick up on these social cues based on if somebody is frowning, if someone is smiling, if the kind of style that they're talking in changes. And ChatGPT and other things can do a surprising amount of this. So these are the main things that I wanted to talk about today. We talked about the nuts and bolts of things like ChatGPT, how they work, that they need these different aspects of data. We went over the history of chatbots all the way from back in the Greek times to actual ChatGPT times. Then we went over a couple of early examples talking about how you can go from some short sentences into something that can generate even more based even on just lookup tables and Markov chains. And we talked about the 4 different components that you would need if you wanted to make your own large language model. The most important being all of the data that you need and where that data comes from, the complex internal machinery required to do it, the GPU compute, which is needed to find a way for that complex machinery to be tuned correctly, as well as very smart training and just kind of like clever ideas on how to get the whole thing done to point it at a meaningful direction. All right, so I hope you all have a great week, and next time we'll talk more about some of the details and all of the amazing ranges of tasks that you can actually do with ChatGPT and other chatbots just like it.